In the last lecture, we have looked at the use of Laplace transforms to solve ordinary differential equations with constant coefficients. So today let's look at applications of Laplace transforms to some physically relevant systems appearing in the real world situations. So the first one is in mechanics, and this is the spring mass system. So here you have a mass attached to a spring. So this is a spring and you have a mass attached at the end. You have a mass body of mass m attached at rest position, and this spring has spring constant k. So the equation of motion for this particle, for this body of mass m, so equation of motion, so if you stretch it and you release, stretch and release, what will be the equation of motion? So this is given by Hooke's law in physics, which says that the acceleration of the particle dx over dt is given by minus the spring constant times the position of the particle. So if you displace from the rest positions, so this is the rest position corresponding to x equals 0. So x is the displacement. So suppose that your new position is here, and from this point to this point, this is your x. So this is the displacement x. So if you displace the body and you release it, then the equation of motion is given by Hooke's law, which is an ordinary differential equation, and you will have some initial conditions. So x0 equals, say, x naught. So this is the displacement x naught at time t equal to 0, and x prime 0 is, let's say, 0. So the velocity of this mass m is 0 when you have stretched it and released it. You can also have some other constant here. So that's the basic equation for Hooke's law. So let me write down here some other conditions. So the first is called damping force. This damping force is proportional to the velocity of the particle. So the proportional to the velocity dx over dt, and it is in the direction opposite to the direction of motion, opposite to the direction of motion. So the damping force let me write d is given by beta dx by dt. So here beta is a positive constant, which is the constant of proportionality when you consider the force as a proportional to the velocity dx by dt. This is the constant of proportionality, and it's a positive constant. So now the equation of motion for this for a particle attached to a spring is m d2x over dt2 is equal to minus kx minus beta dx over dt, because both these forces, so this is Hooke's force and this is the damping force, they are both opposite to the direction of motion, so that's why we have a minus sign in front of both of them. We could also have time varying force, external time varying force, time varying force. So this is given by some function f of t, and in this case the equation of motion is given by m d2x over dt2 is equal to minus kx minus beta dx over dt. So this is the again the Hooke's law and damping force, and you have plus f of t. So f can be positive or negative depending on t, and so it can change, the direction of force can change with time. So here you can take the initial condition x0 as x0 and x prime 0 as v0. So this is the case when you have both a damping force and an external time varying force. External time varying forces can also be present without damping forces, so in that case beta will be taken to be 0. So here I can just write beta greater than or equal to 0. Beta equal to 0 means there is no damping force. So as an example, we can take m to be 1, k to be 6, beta to be 4 and ft to be 0. So this means that there is no damping force present, there is no external force present in this system, and with external initial conditions x0 equals 1 and x prime 0 is 0. So the equation of motion in this case is just d2x over dt2 is equal to minus 6x minus 4 dx by dt. So with x0 equals 1 and x prime 0 equals 0. So now take the transformed equation. So this gives you s square. So again take xs to be the Laplace transform of xt. So then s square x s minus s x0 minus x prime 0 is equal to minus 6xs minus 4 sxs minus x0. So this is the Laplace transform of d2x by dt2. This part is the Laplace transform of 6x, and this part is the Laplace transform of dx over dt. So we get this transformed equation. Now we can simplify because x prime 0 is 0, so this is 0, and x0 is 1. So here we have 1 and here we have also 1. So we get s square xs minus s is equal to minus 6 times xs minus 4s times xs plus 4. Therefore, if we collect the terms with xs and on the left side, we get s square plus 4s plus 6 xs equals s plus 4, and this gives you xs equals s plus 4 over s square plus 4s plus 6. Now we can use partial fractions, or we can simplify also. So let's try to compute the inverse Laplace transform for capital XS. Now we can rewrite XS as s plus 4 over s plus 2 whole square plus 2, and so in fact it turns out that there is no need to use partial fractions, because this is easily computable. The inverse Laplace transform can be easily computed by simply writing this as s plus 2 over s plus 2 whole square plus 2, and the second term is simply 2 over s plus 2 whole square plus 2. Now these two terms in the sum can be easily inverted, and the inverse Laplace transform, for example, for the first term is s plus 2 whole square plus 2, which is nothing but s plus 2 whole square plus root 2 square cosine of square root 2t, and there is a shift of e to the power minus 2t. So this is for the first term, and similarly for the second term, L inverse of 1 over s plus 2 whole square plus square root 2 whole square, and this is nothing but 1 over square root of 2 sine of square root 2 t, because this is of the form 1 over a times a over s square plus a square, and this part is the inversion for this part is simply sine function. So we get 1 over square root t sine square root t, but again there is a shift e to the power minus 2t because there is a plus 2 here. So in the end we will get inverse Laplace transform of xs is equal to e to the power minus 2t cosine square root 2t plus 2 over root 2, which is simply square root of 2, e to the power minus 2t sine of square root 2 times t, and this is your xt. So in this case the solution is what's called this is called a damped oscillatory solution, because the graph of this solution xt looks something like this. So the graph starts out big and then it oscillates, but the amplitude of oscillation dies out as t goes to infinity. So in fact the enveloping curve dies out to 0 as t goes to infinity. So this is called a damped oscillatory solution because it oscillates like this between positive and negative parts. So in this case we can easily solve it, but there can be more complicated functions or more complicated systems given by external forces, which we will see next. Now let us consider the following example for an external force Ft. So if we look at the graph, this force is going to be a constant when t equals to 1 and t equals to 2. So in between these two time frames the graph of the function is constant at value say f naught, and it's going to be 0 outside these two, outside this interval from t equal to 1 to t equal to 2. So in this case one can write the external force as a difference of Heaviside step functions. So we can write this as f naught times the unit Heaviside step function with variable t minus 1 and Heaviside step function with t minus 2. So let's check that ft is giving the same value. So if t is between 0 and 1 then the Heaviside step function is 0, and also so the first term, this is 0, this part is 0, and also this part is 0, because for both variables you get a negative value when t is less than 1. So both are 0, so therefore this is 0. Now if 1 less than or equal to t less than or equal to 2, then the first term is 1 now, this is 1, but the second term is still 0, and so let me write less than 2 here, and so you get 1 times f naught, which is f naught. And now if t is greater than or equal to 2, then you get 1 on both terms. This is also 1 now, and so again you will get 0. So this is exactly the graph that we are dealing with, and this corresponds to the application of a constant force F with magnitude f naught for 1 second starting at t equal to 1 and ending at t equal to 2. So then the equation of motion can be written as, so let me further let me take the same values as the first example. For m1, k was 6 and beta was 4. So in this case we get d2x over dt2 is equal to minus 6x minus 4 dx over dt plus f naught u t minus 1 minus u t minus 2. Now if you take the transformed equation, then you will get, for these 3 terms it's exactly the same as the previous example. So you get s square xs. I should say that the initial conditions are also the same. So x0 was 1 and x prime 0 was 0. So on the left hand side you get s square xs minus s, and on the right side you get 6 times xs minus 4 times sxs minus 1 plus f0, and now you take the Laplace transform for the Heaviside step functions. So the first term will give you e to the power minus s over s, and the second term will give you e to the power minus 2s over s, and so we can simply write it as e to the power minus s minus e to the power minus 2s over s. And now we can collect the terms with xs on the left side. So we get s square plus 4s plus 6 times xs, and on the right side we will get s plus 4 plus f naught times e to the power minus s e to the power minus 2s over s. So if we simplify, we get the following expression for xs. So the first term is simply the one we got before, and we had computed the inverse Laplace transform for this, which was s plus 4 over s square plus 4s plus 6 is the inverse Laplace transform was e to the power minus 2t cosine square root t plus root 2 sine of square root 2t. And now for the second term, we have again two separate terms, and we can use for each term the convolution formula, convolution theorem, to compute the inverse Laplace transform for each of these. So for example, for the first one, e to the power minus s over s times s square plus 4s plus 6, this is equal to the convolution of the inverse of e to the power minus s over s and the inverse Laplace transform of 1 over s square plus 4s plus 6. And so for the first, this is just the unit Heaviside step function at 1, and the second one, this is simply given by, so this is 1 over s plus 2 whole square plus 2, and so this is equal to, the L inverse is equal to 1 over square root 2 sine of root 2 t. So there should be an e to the power minus 2t also, and so in the end we get the inverse Laplace transform of xs, which is the solution xt. So the first term is e to the power minus 2t cos square root 2t plus root 2 sine square root 2t plus f naught times the convolution of the Heaviside step function at 1, and then the function e to the power minus 2t sine of square root 2t over root 2, and the third term is minus f naught Heaviside step function at 2, and with the convolution e to the power minus 2t sine of square root 2t over root 2, and this is our solution. So also in this case we have where we have an external force acting for a short period of time, but with a constant value, we can model it using the Heaviside step functions, and we can solve it using convolution theorem. Another kind of physical situation arises when there is a large external force at time t equals a. For example, a strong blow of the hammer has been hit to the massive particle that is attached at the spring, and so to model this kind of forces, we use so-called Dirac delta function. So when we are talking about a large blow at t equal to a, so let's say this is t equal to a, and we think of our force as acting from a to t equal to a plus h for some h small and positive, and with the magnitude of this force is proportional to 1 over h. So the height of the graph is going to be quite large as h goes towards 0. So we have this kind of situation. So the this height is 1 over h. So as h goes to 0, this height becomes larger and larger as h goes to 0. So this kind of function can be written as fh at t minus a equals 1 over h for a less than or equal to t less than or equal to a plus h and 0 otherwise. So we can try to consider what happens when you take the Laplace transform for such a function. So the Laplace transform of fh, so here again h is positive, fh of t minus a, this is equal to the integral from a to a plus h 1 over h e to the power minus st dt. So one can easily compute this, and you get 1 over h on the outside, and you will get e to the power minus sa minus e to the power minus s a plus h over s. And then one can take the limit as h goes to 0 of this Laplace transform. Let's call this fs with a subscript h. So fhs, this is nothing but 1 over s times the limit as h goes to 0 e to the power minus s a minus e to the power minus a plus h over h, and this is nothing but the negative of the derivative of e to the power minus sx. So this is 1 over s negative of the derivative of e to the power minus sx evaluated at x equal to a. So you will only get e to the power minus as. So we see that in the limit the Laplace transform gives you e to the power minus as, and it often is useful to think of the Dirac delta function. So we can think of the Dirac delta function as defined by the limit delta t minus a. This is the notation for the Dirac delta function. This is notation, and this is equal to the limit, I am putting it in quotes because this limit is not well defined, fh of t minus a, because this will give you plus infinity at t equal to a and 0 otherwise. So this so called function is not really defined at t equal to a. So this Dirac delta function is not a proper function in the usual sense of the term, and it's called it is a generalized function. It has the property, two important properties. So the first property is that the integral of 0 to infinity delta of t minus a dt, this is equal to 1. This is because the area, this area is simply h times 1 over h, this is 1. So even as h goes to 0, the area remains constant, and so as if you take the limit inside formally, then you get this property. The second property is that 0 to infinity delta t minus a ft dt equals fa for any piecewise continuous function ft on 0 infinity. So it only gives you the value f of a. We saw that in the case here, this is our f of t, then it gives you f of a, which is e to the power minus as, and you can do the same analysis with any other function, not necessarily e to the power minus st, and you will get the same answer, which is f of a. And this is called the sifting property, not shifting but sifting with an s, sifting property of the Dirac delta function. Another property is that formally the delta function delta t minus a can be thought of as the derivative of the Heaviside unit step function at a. So this is because the Laplace transform of delta t minus a equals minus s, while the Laplace transform of the unit Heaviside step function is e to the power minus as over s. So suppose, assuming that the derivative theorem holds, we get formally, by formally I mean it's I'm not talking about in a rigorous mathematical sense, but just by intuition we get the derivative of the unit Heaviside step function is equal to delta t minus a. So these are the important properties of the delta function, and so we can use this to model large blows for small intervals of time, very small intervals of time, or even when you have an electrical circuit, you can, and there is a large current flowing for a very small time, then you can also model it using the delta function. We can have other applications, for example to electrical circuits via Kirchhoff's law. Here we have a circuit where there is an inductor L of inductance L, then we have E is a battery with electromotive force of E volts. So E, this is a battery, this is an inductor, this is a resistor, and this is a capacitor, and current is supposed to flow through this circuit when this switch is closed. This is a switch, and so the equation for the flow of charge, Q is charge. So this is the equation of flow of charge or current. This is given by this equation, in this is a second order ordinary differential equation with constant coefficients, and it is of the same form, this is of the same form as the spring mass system that we have seen before. So this is an initial value problem with the mathematically the same set of equations. So one can, given these are all constants, L is an inductance, E is the electromotive force or E volts, R is the resistance, and C is the capacitance, and these are considered to be constants as far as solving the differential equation goes. E can also be dependent on the time t, as we have seen. This is a corresponds to the external force, and you can also have for example a large flow of current passing through the circuit for very small periods of time, which can then be modeled using delta functions as well. So in principle we have the same set of equations and they can be solved in the same way as we have done for spring mass systems. Now let's come to this boundary value problems. So as an example, we can take the differential equation y double prime plus lambda square y equals cos lambda t. Here one of the conditions is y0 equal to 1, but the other condition is given at a different point, and it's still for y and not the derivative. Y of pi over 2 lambda equals 1. So we can think of the solution as limited between y equal to 0 and t equal to 0 and t equal to pi over 2 lambda, and so these are boundary values for the function y, and these values are given so that we can find out the constants that appear when we try to solve the differential equation using Laplace transforms. So let's try to solve this. So the transformed equation looks something like this. So for the first term you have s square ys minus s y0 is just 1, so just s, and then minus y prime 0. So this is not known, so we can let y prime 0 equals some constant alpha to be determined, and I am just going to put alpha here, and then plus lambda square ys, and on the right hand side you will get s over s square plus lambda square. So therefore s square plus lambda square ys equals s plus alpha plus s by s square plus lambda square. And now if you take s square plus lambda square to the right hand side, this is s plus alpha by s square plus lambda square plus s by s square plus lambda square whole square. And now we can try to invert this ys. So the inverse Laplace transform for ys. So the first term is s by s square plus lambda square. The second term is alpha times the inverse Laplace transform of 1 over s square plus lambda square, and the third term is inverse Laplace transform of s over s square plus lambda square whole squared. So in this case the first term is simply cos lambda t, the second term is simply alpha sin lambda t. The convolution of cos lambda x with sin lambda x over lambda evaluated at t. So because this can be written as two functions, s over s square plus lambda square times 1 over s square plus lambda square, and if you evaluate this you will get sine of so this convolution, the whole convolution gives you t by 2 sine of lambda t. So now this is still undetermined, so we will use the fact that y at pi by 2 lambda equals 1. So this implies, so this is our yt. So this implies that if you plug in this value pi by 2 lambda in this equation, you will get 1 on the left hand side. We will get first term is cos of pi by 2, this is 0. Then you have alpha sine of pi by 2, this is 1, and the third term is t by 2 lambda, so 1 over 2 lambda times pi over 2 lambda sine of pi by 2. So this is also 1, and so we get alpha is 1 minus pi by 4 lambda squared. This was our y prime at 0, and so now we have solved this undetermined coefficient as well. and so the solution is complete.